So the nature of the circumferential stress is tensile. The nature of the longitudinal stress is also tensile. Okay. So and out of these two number of stresses, important stress is circumferential stress, because the magnitude of the circumferential stress is 2 times greater when compared to magnitude of the longitudinal stress. Okay. Yes. So probably let us proceed further. In today's class, we will have some discussion with regard to I lapis AC and so we will see. We will have some discussion regarding thick cylindrical shells. Right. So now I'm sure, I hope you could able to see this writing pad, right? Is it clear? Are you able to see the writing pad?
Yes, sir.
Okay, that's fine. Yeah. So lecture number is 39. So today we will have some discussion with regard to thick cylindrical shells, right? Okay. So probably important governing equations are Ramis equations. So probably whatever equations you have already derived with regard to thin cylindrical shells, they will not be sufficient. Okay. So here, if you see, probably the main important difference is that in case of thin cylindrical shell as well as thick cylindrical shell, okay, the thickness dimension is almost negligible when compared to inside diameter. So probably I can say that if d by t, okay, so of the order of 21, something like that. Okay, so if thickness is 1 unit, inside diameter of the shell, if it is 20 units, probably you say that it is a thin cylindrical shell. Okay, so probably if I say d by t 5, I can say that it is thick cylindrical shell. When compared to inside diameter, the thickness dimension is 1 unit. So it is thick cylindrical shell. Okay. So 5 to 10, probably I can say that. Fine. Admit. So this is around 5 to 10. I can say that it is thick cylindrical shell. So in case of thin cylindrical shell, you know, the circumferential stress is generated inside the shell material, and then longitudinal stress is generated inside the shell material. Okay. But whereas in case of thick cylindrical shell, okay, in case of thick cylindrical shell, probably if you see the stress, circumferential stress is uniform over the thickness of the shell. If I say that this is the thickness of the shell, so the magnitude of the circumferential stress is uniform. Okay, in case of thin. I mean to say that when you move from inner surface of the shell to the outer surface of the shell, the magnitude of the circumferential stress is same. That is what I wanted to say. Or otherwise, if I draw a diagram, say like this, okay, so whatever magnitude of the circumferential stress here, the magnitude is same. That is what? Thin cylindrical shell. Right? But suppose if I do consider thick cylindrical shell, okay, so because of more thickness of the shell, I mean to say that the thickness dimension is comparable when compared to inside diameter of the shell. Okay. So probably if you move from inner surface of the shell to the outer surface of the shell, the variation of the Hooke stress is not uniform. In case of thick shell, sigma C is not uniform. We will see how it is varying probably. If I derive the governing equations, automatically we will be knowing how circumferential stress is varying over the thickness of the cylindrical shell. Okay, so no problem. Let us imagine that I have a thick cylindrical shell. Just imagine that. Okay, so it has got maybe this blue colored one is inner radius of the cylindrical shell. This another blue color is outer radius of the thin cylindrical shell. Okay. So once again, the purpose of the thick cylindrical shell is that to store the fluid under pressure. Okay, it means that more magnitude of the you can store more pressurized fluid inside the cylindrical shell. Okay, the limitation in case of thin cylindrical shell is that probably if you go on increasing pressure of the fluid corresponding to some limit, it's going to fail. So the load bearing capacity in terms of pressure, if it is some maybe 10 times atmospheric pressure, here if you do increase the thickness of the cylindrical shell, probably you can without failure of the shell material, so you can go up to some 15 megapascals, 25, something like that. Okay. So probably you just imagine that I have a thick cylindrical shell. It is subjected to some fluid under pressure. So Pi is the internal fluid pressure. So Pi is internal fluid pressure. Okay. Right. Sometimes it may be subjected to only fluid, maybe fluid pressure over the inner surface of the shell, or sometimes it may be subjected to fluid pressure both inside as well as outside. No problem. So you can also see different boundary conditions. Yeah. Now, what I am doing, you just imagine that you have a thick cylindrical shell and it is subjected to fluid under pressure over the inner surface of the shell. Right. So within the material of the shell, I wanted to take some elemental ring. This red one indicates elemental ring. Okay, so maybe this elemental ring has been separated, right? Okay, so probably if I pick out some small elemental ring from the material of the thick cylindrical shell, so over the inner surface of the elemental ring, it is subjected to a radial stress of magnitude sigma r. I'm writing sigma r is radial stress. Okay, at a distance of r. At a distance of r. And the outer fiber is subjected to a stress of magnitude because whatever elemental ring I have considered, this is in the state of equilibrium. Okay, so in the radial direction, I have considered some incremental stress. So the stress at the outermost fiber is sigma r plus d sigma r. At what distance? R plus dr. Okay, right? Because these stresses are generated inside the shell material because of fluid under pressure. Right. Now probably if I take some, you just imagine that. So probably if you take some static equilibrium equation. So one is because of fluid pressure, radial stress will be generated inside the shell material, and because of the fluid pressure, circumferential stress is also generated inside the shell material. Sigma C is circumferential stress. Okay. So this stress is generated, sigma R is generated in the radial direction. This is generated in the circumferential direction. And you have one more type of stress which is generated inside the shell material, the longitudinal stress. Yes, longitudinal stress. So these are the different types of stresses which are generated inside the shell material. One is sigma R, another one is sigma C, another one is sigma L. Totally, there are three number of stresses: circumferential, radial, and longitudinal stress. Okay. Now, probably before I do derive the governing equations, probably one important assumption is material is homogeneous. Material is homogeneous. Another important assumption is plane sections remain plane before and after loading. Okay. This is another important assumption. Plane sections remain plane before and after loading. Okay. And another assumption is that material is loaded within the elastic limit. Loaded up to elastic limit. Right? Yes. Now, whenever the thick cylindrical shell, if it is subjected to fluid under pressure, you have seen that there are three variety of stresses which are generated inside the shell material. So if you recall assumption number 2, plane sections remain plane before the loading as well as even after the loading. Okay, so probably that says that longitudinal strain is constant. So probably, so how do I calculate longitudinal stress? If you have three number of stresses, sigma C, sigma L, and radial stress. In general, circumferential stress is tension, longitudinal stress is tension. This is compressive in nature. So if I write an expression for longitudinal strain, this is the sigma C and minus nu by E, and because radial stress is compressive in nature, minus of minus plus. So this equation I can write. Right. Okay. So the expression for longitudinal strain, right? So probably I can say that this is constant. So this is also constant. So if I take maybe from the second term, third term, also constant, right? If I also take nu by E constant, minus nu by E as common, sigma C minus sigma R is equals to another constant. So probably I'm writing here sigma C minus sigma R. I'm writing some other constant. Okay. where A is also constant, right? So from assumption number 2, I have got one important equation as sigma C minus sigma R as 2A, right? Now probably, so from the equilibrium equation, so probably if you go on increasing the pressure of the fluid corresponding to some pressure, without any doubt, the elemental ring is going to fail. Not only elemental ring, that entire thick cylindrical shell is broken into 2 halves along the longitudinal direction. So probably I can write this equilibrium equation. So here you have, maybe this is not, so I can probably I can apply another static equilibrium equation. What is that? So probably if you take half of this elemental ring, probably if I take okay, it is subjected to our inner surface, it is subjected to radial stress. Here it is subjected to sigma R plus d sigma R. And here you have circumferential stress. Right, what is the dimension here? This is R. This is also R. The thickness of the shell is dr. The thickness of the shell is dr. Okay. Right. So probably if I write another equilibrium equation from this, so probably let me take this. Yes. Yes. Now probably if I write another static equilibrium equation from this, that is resisting force is equals to bursting force. Resisting force equals to bursting force. What do you mean by resisting force? Because of the internal fluid pressure, okay, stresses will be generated inside the shell material, that is circumferential stress. Okay, the circumferential stress is responsible to withstand the fluid pressure. Okay, and because of that, not only circumferential stress, radial stress is also generated inside the shell material. Right. So probably now you see here, what is resisting force? Resisting force perpendicular to this. You just imagine length of the cylinder perpendicular to this paper. Okay. So what is the area of cross section? Perpendicular to the paper, you have a length of the cylinder as L. So L into a thickness. This thickness is dr. Okay. So L into dr this side, you have L into dr. So probably 2L dr multiplied by circumferential stress. This is the resisting force. Stress multiplied by resisting area of cross section. So circumferential stress multiplied by area of cross section is length of the cylinder multiplied by thickness of the cylinder. So L into dr plus L into dr is that one. Now probably here if you see in the upward direction, if you resolve this radial stress, one in the vertical direction, okay, sigma R if you resolve. So probably, okay, I want sum of the forces only in the vertical direction equals to 0. Okay, so the resisting force is sigma c, and probably if you resolve the sigma r, you have vertical component of force as well as horizontal component of force. Okay, I'm not worried about horizontal component of force. I'm just worried about only vertical component of force. So that stress multiplied by, okay, that stress is acting. Okay, this probably that stress is acting over the projected area. What projected area? So corresponding to inside projected area corresponding to inner radius of the elemental ring. So what is that? So in general, if you have shell diameter is d, l, projected area is dl. So here 2 times r. Okay, l. That is the projected area. Stress multiplied by projected area. Okay, if you take upward force as positive, and probably you have one more component of force which is acting in the downward direction, that is sigma r plus d sigma r. Incremental radial stress is acting. Okay, now you just see projected area until this extent. So here r plus dr is there on one side, you have r plus dr. So 2r plus 2 times dr. So probably if I take common, r plus dr. Okay, so into L. That is the resisting area of cross section. Okay, that is the projected area corresponding to the stress which is acting over the outer elemental ring. Now probably if you simplify this, so I can cancel out 2L is there, everywhere 2L is there. Okay, so let me rewrite this equation. Sigma c into dr. Okay, r times sigma r I am writing. So let us simplify. 2 into 2, 4 terms, you will get 4 terms. So r times sigma r minus dr times sigma r minus r times d sigma r minus dr d sigma r. Okay, so these are the, you check it out. Same చేయట్లేదు తర్వాత so just check it out. R into sigma r, dr into sigma r. Let me check it out. R into d sigma r. That's correct. So probably these first 2 terms will be getting cancelled, and dr itself is very, very small quantity. So multiplication of these 2 small quantities can be neglected. Dr d sigma r. So probably okay. So let me. So it is dr times sigma r. So r times d sigma r. That is what I have done. Right. So still let us go further. So probably here dr is there. Here also dr is there. Let me take one side. Sigma r dr minus r times d sigma r. Okay. If I take r as common, sigma c plus sigma r dr minus r times d sigma r. Okay, right. So this is what I have got. Probably let me name this as equation number 2. Okay, but equation number 1, if you see, sigma c minus sigma r, they two are separated by 2a. I can use that. So probably from equation number 1, 2a. So probably in place of sigma c, in place of sigma c, I can write sigma r plus 2a. So here by substituting this equation 2, probably so sigma r plus 2a plus sigma r to dr. So this is what I have got. Okay. Now probably if I take sigma 2 times sigma r, if I take 2 as common, sigma r plus a into dr minus r times d sigma r. That is what I have got. So check it out. Okay. Right. So if I separate the variables separating the variables separable. So probably, so here I have d sigma r by dr, d sigma r by sigma r plus, okay, let us assume that this term I have taken other side, okay, equals to minus 2 times dr by r. This is what I have got. Check it out. D sigma r by sigma r plus a equals to minus 2 times dr by r. So probably, let me name this as equation number 3. Integrate equation 3 both sides. Okay, so the integration of maybe it is this side, so probably minus 2 times log r. Okay, so probably let me add some integrating constant. So here it is log sigma r plus a. Check it out. By integrating both sides, right? So from this, I can write the equation as probably, so this you can write b by r square, okay? Log a plus log b, right? It is log b minus log r square. Log r square can be written as 2 times log r. So if I cancel out this log term, sigma r plus a equals to b by r square. So probably the expression for radial stress is b by r square minus a. This is very, very important governing equation as far as thick cylindrical shell is concerned. Let me name as equation 4. Okay. And from equation 1, I said that equation 1 is, if I rewrite equation 1 once again, sigma c, sigma r, they two are separated by 2a. Okay, a and b are Lami's constants. Lami's constants. Okay, so they can be evaluated from the boundary conditions. Probably you are going to see slightly after some time. Now you have got an expression for sigma. Now probably you substitute, so probably sigma c. In place of sigma r, I am writing b by r square minus a. So let us simplify further. So sigma c minus b by r square minus plus a is 2a. So if I write an expression for sigma c, right, what do I get? Yes, this is another important expression. Okay, these equations are very, very important. So one is equation 4, another one is equation 5. Okay, so let me write these expressions once again. Expression for circumferential stress is b by r square plus a, and expression for radial stress is b by r square minus a. Okay, these are equations. These equations are called Lami's equations. Lami's equations. Okay, so with help of these two equations, you can find out circumferential stress at any cross section within the thickness of the shell, or at any radial fiber. You can calculate magnitude of the circumferential stress as well as radial stress. You can say that at any radial fiber or at any radius, you can calculate the magnitude of the circumferential stress, the magnitude of the radial stress. Okay, probably maybe at what location the circumferential stress is becoming maximum, at what location the radial stress is becoming maximum, you can calculate. Okay, don't worry regarding A and B, they can be calculated very easily. Right? And another important point from these Lami's equations, if you see, so the variation of the circumferential stress here, b by r square, it's parabolic variation. Okay, so over the thickness of the shell, circumferential stress is varying parabolically. Parabolic. Not only sigma c, sigma r, sigma c, they do vary parabolically over the thickness of the shell. Okay, so probably if I work out one numerical problem, I'm very sure that each one of you can feel more comfortable, right? So this derivation is very, very important. These are all called Lami's equations. So this is the procedure to be followed to calculate, to derive Lami's equations. Okay, and another important point is that the nature of the circumferential stress is tensile. The nature of the radial stress is compressive. Very, very important. Okay. So this is tensile. This is compressive in nature. And probably now you can work out different variety of problems. So case 1, case 2, case 3. Let us see. Now you just imagine that I have a thick cylindrical shell. Just okay. If this thick cylindrical shell, if it is subjected to some fluid under pressure, it is PI. Just imagine I am unable to draw here PI. Okay. So sometimes it may be subjected to pressure over the external surface of the shell. So here case 1 is that, okay, maybe inside and outside it is subjected to fluid under pressure. Okay, shell is subjected to fluid pressure at inside as well as outside. Okay. So the magnitude of the pressure over the inner surface of the shell is represented with Pi. The magnitude of the pressure over the outer surface of the shell is subjected to P0. It may be, okay, probably. You just imagine that the radius of the inner surface of the shell is R1, radius of the outer surface of the shell is R2. So you can work out, no problem. And another one, probably, you just imagine that, okay, so you may have only fluid pressure over the inner surface of the shell. Fluid pressure only inner cylinder. Okay. So the inner surface of the shell only subjected to fluid under pressure whose magnitude is Pi. So here P0 is 0. Right. Now probably if I draw one more case, so you may have pressure over the external surface of the shell of magnitude is P0. So here Pi is 0. So P0 is existing. This is what case 2, case 3. Right? Now I am repeating case 1. The inner surface of the shell is subjected to some fluid under pressure whose magnitude is Pi. So it is maybe, for example, as I mentioned earlier, maybe this Reliance people, ONGC people, they are extracting natural gas from the bed surface of the ocean. So when they are laying pipe, say for example some pipe, so this pipe is inserted within the ocean water. So some fluid is natural gas is transported, and the external surface of the shell is subjected to water waves. So you can have such type of example. Okay. And to this probably this LPG gas cylinders and then whatever water tanks and maybe, okay, you can have big water tanks. I told very clearly the capacity of the water tank is approximately of the order of 1 lakh liters. So design of the tank plays an important role, right? And maybe probably here, if the external surface of the cylindrical shell, if it is exposed to atmospheric pressure, you can take it as P0 is 0. Right? Likewise. Okay. Now in all these cases, probably what are all boundary conditions you can avail? So in all the 3 cases, same equations you do use, no problem. So one is, now as far as boundary conditions are concerned, governing equations are same. Governing equations are same. Now, so let me write boundary conditions for this case. Boundary conditions are related to this stress. So V by R square minus A. So boundary condition 1, because how many number of constants are there? 2 number of constants are there, A and B. So you require 2 number of boundary conditions. First boundary condition, because case 1, the shell is subjected to fluid under pressure. At what radius? At a radius of R1. So boundary condition 1, at R equals to R1, okay, sigma R equals to pressure of the fluid over the inner surface of the shell. This is the boundary condition 1 I can use. At R equals to R1, sigma R equals to P of I. Now boundary condition 2, exterior surface. At R equals to R2, once again it is subjected to some pressure. Some fluid is acting over the exterior surface of the shell, P0. Yes. Okay. You can substitute these two boundary conditions in this equation. Let me write some equation A. You substitute these two boundary conditions in equation A so that you get two number of equations. You solve those two equations and calculate value of A and B. So once you do calculate value of A and B, you back substitute those A and B in this equation A and also in this equation. Okay, these equations. So if A and B are known, just it is function of R. So probably wherever you are interested to calculate, you can calculate the magnitude of the circumferential stress as well as you can calculate the magnitude of the radial stress. Now coming to this, what are the boundary conditions I can use? Now it is just subject to pressure over the inner surface of the shell only. So at R equals to R1 Pi, sigma R equals to Pi. This is what I can use. Now boundary conditions too. Two boundary conditions are very much required. Otherwise, you can't probably you have to get two number of equations. So at external surface of the shell, there is no pressure. So sigma R equals to 0. Right. So sigma R equals to 0. That's all. These are the boundary conditions I can avoid because the inner surface of the shell only is subjected to fluid pressure. At what location? At a distance of R1. So at R equals to R1, sigma R equals to Pi. This is given. And over the external surface of the shell, there is no pressure. So sigma R equals to 0. You substitute these two equations in this equation A and solve for A and B. You back substitute A and B so that maybe you can calculate circumferential stress as well as radial stress. Now see here, what boundary condition I can avoid? So is there any fluid over the inner surface of the shell? There is no fluid. So at R equals to R1, sigma R is 0, no pressure. And another is condition 2. At R equals to R2, sigma R is equals to P0. Okay, that's all. It's very interesting, very simple. So you can do it. Okay. You have any doubt, anybody? Any doubt? So, if there are no doubts, probably let us proceed further. So let us work out this problem. You may be given any case. You may be given case 1, case 2, case 3. Just only thing is that boundary conditions are slightly different. Everything is same. So let us work out one numerical problem. Write down this problem. Write down each one of you. write down. Is subjected to an external pressure of 40 megapascal. But the internal pressure is 120. So calculate circumferential and radial stress. Radial stress at inner and outer surfaces. Yeah. You just read the problem, each one of you. That's the problem given. The internal and external diameter of a thick hollow cylinder are 8 centimeters and 120, 12 centimeters respectively, 8 and 12. It is subjected to an internal pressure of 40 megapascal, external pressure 40 megapascal, when the internal pressure is 120 megapascal. Calculate circumferential and radial stress at inner and outer surfaces. Okay? Yes. Just let us see. So the given data, just write down very clearly. I'm assuming inside diameter is D1, 8 centimeter. So it is to R1, right? So from this R1 equals to 8 by 2, 4 centimeter, that is same as 40 mm. Right? And outside diameter, I am assuming D2. Okay, it is 12 centimeters. It is 2R2. So from this R2 is 12 by 2, 6 centimeter is same as 60 mm. Okay. And so it is subjected to an external pressure. So external pressure is represented with P0. External pressure. How much it is given? 40 megapascal. 40 megapascal is same as 40 Newton per mm square. And also it is subjected to an internal pressure of 120. So Pi. So internal pressure. It is 120 Newton per mm square. Okay, that's what given. So probably. So let me draw a schematic diagram. So probably, okay. I want to draw a big circle. You also try to draw a big circle. Okay. Just imagine, say for example, I may not be so accurate because I am using this writing pad. I hope you could be able to do a good one. Okay, just imagine that. Okay, now let us still. So this is the cylindrical shell. Okay, it is subjected to fluid under pressure. These dots are represented with fluid pressure. We just mention some pressure. How much pressure is acting? Of magnitude Pi. And also the external surface of the shell is also subjected to some fluid pressure. This is represented with P0. So internal fluid pressure is given 120, external fluid pressure is 40. And this this data. So probably from here to here, you know, I'm assuming that R1. Here it is O. So from here to here, it is R2. So R1 is inner radius of the shell. Inner radius of the thick cylinder. Okay, R2 is outer radius of the thick cylinder. It's already given 40, and here it is 60. That's all. Okay. Now it's very simple. Okay. Now immediately you just draw, or maybe probably let me take this schematic diagram once again. Uh, yes. Okay. Yes. Now to write down Lamis equations. Lamis equations are sigma C is equals to B by R square plus A, and sigma R B by R square minus A. These are the Lamis equations, right? So probably boundary conditions are related to only radial stress. You have to be extremely careful. Now probably the cylindrical shell is subjected to internal fluid pressure as well as external fluid pressure. So external external fluid pressure so you just work out some problem with this pen. You use the boundary condition 1 as at R equals to R1. At R equals to R1, that is at 40 mm, sigma R equals to 120. Make a note of that. At R equals to R1, that is 40 mm, sigma R equals to 120. That's boundary condition 1. Now one more boundary condition at R equals to R2. At R equals to R2, that is at 60 mm, R2 equals to 60 mm, sigma R equals to 40 Newton per mm square. Okay? Yes. Now, so substitute these two boundary conditions to equation number 2 and solve for A and B. Let us see, what do you get? So boundary condition 1 is at R equals to R1, that is 40 mm. Sigma R is how much? I think it is 120. 120 Newton per mm square. Right? You substitute this boundary condition to equation number 2. So sigma R is 120. Okay. In place of R, R1, that is 40. Okay. Let us write equation number 3. Now, what is boundary condition 2? Boundary condition 2 is that at outer fiber R2, that is 60, the pressure over the external surface of the shell is, I think it is 40. Yes, 40 Newton per mm square. You apply this boundary condition to equation number 2. So 40 B by R square, 60 square minus A. Yes, now you have got two number of equations. Solve for equation 3 and 4. Solve for 3 and 4. Tell me the values of A and B. Take some time, no problem, 2 to 3 minutes. Come on, quickly do it. Anybody completed? What is the value of A? What is the value of B? What is the value of A and B? Very simple. Sorry. చెప్పండమ్మా, ఏ వాల్యూ ఎంత, బి వాల్యూ ఎంత? One of you tell me. In
339 Murali Krishna. What is A and B?
Tell me the values of A and B. Murali Krishna, 39. Aina Murali Krishna unnava? Action పెట్టేసి పర్వాలేదు. 1 week action. మాట్లాడామయ్యా. 1 week action పెట్టి చూపిస్తాం, ఇంకేం లేదు. వాల్యూ ఆఫ్ ఏంటి చెప్పు, క్విక్ గా రెస్పాండ్ అవ్వాలా. లేకపోతే ఏమైతుందంటే వారానికి బదులు 2 వారాలు పడతాయి యాక్షన్. అంత ఏం ఉండదు. చెప్పు, ఏ అంత బి అంత తొందరగా చేయవయ్యా. ఎంత వచ్చిందా శ్రీకాంత్, ఎంత వచ్చింది చెప్పమ్మా.
Yes,
24 is correct. B ఎంతమ్మా?
2,30,400 వచ్చింది సార్.
Very good, exactly correct. Yeah, now you put off your speakers. So that is the value of A and B. A is 24, B is 2,30,400. Yes, now probably you can calculate wherever you are interested, you can calculate the stress. So probably now let me write a generalized expression for circumferential stress. So that is B by R square plus A. Just I have rewritten equation number 1. Now at what fiber you are very much interested? I want circumferential stress at inner fiber. Okay, what is that value? Value is 40 mm. What is that? In place of R, you just substitute 40. You know the value of A, you know the value of B, that's all. So 2,30,400 by, in place of R, radius of the innermost fiber. Yes, you calculate the value. And similarly, calculate circumferential stress at the outermost fiber. What is the value? 60. Very simple. Once you have got A value of A and B, it is just function of radius. Wherever you are interested, you can calculate the circumferential stress. Not only circumferential, you can also calculate radial stress. Do that. Take some time. Take some time. So circumferential stress. So next one is radial stress. Quickly do it. Each one of you quickly do it. Roll number 7. What is the value of circumferential stress at the innermost fiber? Emma?
Sigma CI 168 megapascal.
168? What are the units?
Megapascal.
Very good. Megapascal or Newton per mm square. So tell me at the outermost fiber?
88 megapascals.
Very good. Now similarly, do calculate radial stress at the innermost fiber as well as the outermost fiber. Okay, A, B are known. Just it is function of radius. That's all. Very, very simple. So the magnitude of the radial stress at the innermost fiber is 40 square. Only difference is that minus. Okay, the outermost fiber. Yes, calculate. Take another 1 or 2 minutes.
సార్ డైరెక్ట్ గా ప్రెషర్ వాల్యూస్ వస్తాయి కదా సార్ అవి.
అది నువ్వు క్యాల్కులేట్ చేయమ్మా, ఎంత వస్తే అంత అంతే వస్తాయి, కరెక్టే. Yes, you will get the same value, correct. At R equals to R1, you will get internal fluid pressure whose magnitude is 120. At R equals to R2, you have external fluid pressure whose magnitude is 40. You have to get the same answer, check it out. If you neglect some digits, probably truncation, you will get this some error. Okay. Instead of 120, you may get 119 something, or instead of 40, you may get some 39 something, or 40 point something something. You have to be extremely careful. Okay. So the radial stress at the innermost fiber is 120, and here it is 40. Okay. Now let us draw the variation of circumferential stress as well as radial stress over the fibers. Now see here. So I have considered thickness of the thick cylindrical shell. So at the innermost radial fiber, you have seen that the magnitude of the circumferential stress is 168. I am assuming, not assuming, 168. So here it is 188, not 188, 88. So the variation is parabolic. This is parabolic. Okay, this way stress is varying over the thickness of the shell. That is parabolic variation of the circumferential stress over the thickness of the shell. Okay, and if you see one important conclusion, the maximum circumferential stress is existing at the innermost fiber. So here only stress is becoming maximum, and you have minimum circumferential stress at the outermost fiber. So when you move from inner surface of the shell to the outer surface of the shell, the circumferential stress is varying parabolically. Okay, and similarly, if you draw variation of radial stress, so at this location 120, here it is 0. Once again, the variation is parabolic. Okay, so this is once again parabolic. This is variation of circumferential stress. This is variation of radial stress. Okay, and sigma c is tension. This is compression. Okay, so this way you can confidently design any thick cylindrical shell. Okay, so you can design any thick cylindrical shell without any doubt. Right? So if you see at the innermost fiber, the magnitude of the circumferential stress is 168. The magnitude of the circumferential stress at the outermost fiber is 88, and radial stress at the innermost fiber is 120. So it's not 0, it is 40. I made a mistake. You're also not telling. It's not 0 here, it is 40 is there. 40 pressure is there. So here some pressure is existing. That is the variation of the radial stress. Here it is 40. Here it is 120. Right? So variation of the radial stress is parabolic. Okay. So these are all very, very important. So probably I'm sure you are very confident of designing the thick cylindrical shells. Okay. So also work out one more numerical problem. When you come to the next class, you write down this problem. I'm also writing. Just take, probably when, not probably, you have to work out these two problems and then bring the solutions. Internal pressure of internal pressure of 50 Newton per mm square. Okay. So calculate sigma C, sigma R at both fibers. Okay. That's all. Okay. Calculate sigma C, sigma R at the inner and outer radii. Okay, a thick cylinder of 125 mm inside radius and 250 mm outside radius is subjected to an internal pressure of 50. That's all. Okay, so you work out and then bring the solution when you come to the next class. So one more is that probably this is a typical problem. Let me see how many number of people you are going to work on this. So a thick cylindrical shell of 150 mm internal diameter is required to withstand an internal pressure of 8 Newton per mm square. Find the necessary thickness of the shell thickness of the shell if the permissible tensile stress in the section is 20 Newton per. This is the problem. That's all. This is the data given. A thick cylindrical shell of 150 mm internal diameter is required to withstand internal pressure of 8 Newton per mm square. You have a thick cylindrical shell. Inside diameter is 150 mm. Thickness of the shell is not known. So this thick shell is subjected to a internal fluid whose pressure is 8. Find the necessary thickness of the shell if the permissible tensile stress of the section is 20. Yes, you do refer Google or something. I want to work out these two numerical problems when you come to the next class. Okay? Yes. So I will stop the discussion here. So probably if you have any doubt, you can feel free to ask. Okay? So tomorrow also we will have some discussion with regard to compound cylinders. It is maybe based on the thick cylindrical shell only. Compound cylinders. Right? So, Masrika, attendance పంపించామా శరత్కి
సెండ్ చేస్తాను సార్.
పంపించేసావా? Okay, very good. Yeah. Any doubt you have? If you have any doubt, you ask me. Otherwise, probably I will close the meeting. Okay, you work out these two problems, not only these two problems, maybe as far as this unit is concerned, you have thin cylindrical shells and wire-wound cylindrical shells are there. Thin spherical shell is there, that takes only 5 to 10 minutes, probably time permits tomorrow or at some time I'm going to cover. You can work out the assignment. Okay, you try to pick out some typical problems from any standard textbook, work out as many number of problems as possible, minimum 10. Okay, you work out some 2 to 3 problems on thin cylindrical shells, 1 to 2 problems on wire-wound cylinders, and 2 to 3 problems on thick cylindrical shell, and 2 to 3 problems on compound cylinders. Probably you submit the assignment probably next week, maybe next week Monday or Tuesday. Okay, this week this entire unit will be completed because I have another 2 more number of classes. So the concept of compound cylinder will be completed. So you work out the assignment. Okay, right. So if there are no doubts, probably I am closing the meeting.
See you.
Permission.